Guys, I wasn't gonna do any more notes and talking through them, but I've heard that you'd rather me talk through them than show them to you, so it's up to you. You can listen to me or you can just look at them. Um, okay, first things first, we have to talk about the double bond because this part is all about reactions and reactions with a double bond. So double bond is composed again of a sigma, this is the sigma bond, and a pi bond. The pi bond goes above and below the axes. Rotation is restricted, that's why we have cis-trans isomerism. And the other thing that's going to happen with these double bonds is that these pi bonds are a little bit easier to break than the sigma bonds. So if you remember before, we were talking about alkanes, and a couple of the different reactions that we talked about with alkanes were combustion. And combustion is, of course, just the alkane reacting with oxygen yields CO2, water. The other reaction that we talked about was called substitution. Substitution is just what it sounds like. One of these gets substituted in, so we end up with chlorine attached here, and then we get hydrochloric acid. So those were the two reactions we already talked about. In this chapter, we're going to talk about two new types of reactions. The first one we're going to talk about is elimination, but the more important one is addition. So we'll talk about both of these. But let's start with elimination because elimination is pretty simple and we don't do as much of it. So for elimination, the first one I want to talk about is elimination. Again, just what it sounds like. It goes away. Elimination of water from alcohols. So remember in this chapter, when you think about water, think about it as HOH, right? Of course, water is H2O, but when you eliminate the OH and you eliminate the H, this is going to be a double bond that's going to form. So you're going to end up with a alkane going to an alkene, and then you're going to pull out water. And again, that's H2O, but a lot of times in this chapter, I'll write it as HOH. Now, this does have to happen at a certain temperature, and it has to happen in excess acid, and I'll get more into that in the next chapter. The other example of an elimination reaction, and there are several different ones, but this is another kind of easy example, is elimination of a salt and water from a haloalkane and a base. So let me walk you through this. First of all, this is the haloalkane because chlorine is the halogen here. This is a base. The base could be NaOH or KOH, I mean, whatever it is. And what happens is the alkane has this halogen attached, so that halogen is removed. The halogen then attaches to whatever proton was, proton donor was there with the base. And then the OH attaches to the H, so water gets eliminated. So again, let me see if I can just kind of draw this out for you so that you can see. But this guy ends up over here, right, as that hydrogen. This one ends up as the other part of the OH over here. And then these two, the chlorine and the potassium, end up over here. Now on to addition reactions. So addition reactions have to do again with the pi bond. It's when the pi bond of the double bond is easier to break apart than the sigma bond. So it is the active site where these reactions happen. Addition means two reactants turn into one product. So the word addition does mean that you're going to add something to it, but you can see here for all of these, you have two reactants that turn into one product. So there's different things that we're going to add here. We can add hydrogen, that's called hydrogenation, halogens, halogenation, hydrogen halides, and water. And I'll walk you through each one of these.
A carbon-carbon double bond or triple bond of an organic compound is broken. The electrons shift to connect to hydrogen atoms, halogens, hydroxides, or other compounds. The connecting with hydrogen is called hydrogenation. Connecting with chlorine is chlorination. And when it's fluorine that bonds with the organic compound, we call it a fluorination reaction. The number of double bonds in an organic compound can be calculated by the amount of gas consumed in addition reactions with hydrogen molecules. These reactions require metal catalysts to break the covalent bonds between hydrogen atoms. Here's an example of an addition reaction. The reactants are propane and hydrogen bromide in a solvent of alcohol. Bromine has much higher electronegativity than hydrogen. In other words, it really wants to take hydrogen's electron. So when hydrogen bumps into the unstable pi bond between the carbons, and its focus is no longer fully on its own electron, bromine takes a chance and grabs hydrogen's electron and runs off. At the same time, hydrogen takes an electron from the pi bond and bonds with carbon. We see that now one carbon is missing an electron. It has a partial positive charge as a carbon cation. Bromine, on the other hand, has an extra electron, forming a negatively charged bromine anion. When the carbon cation tries to get an electron back, it seizes an electron held by the bromine anion, thus bonding and creating two bromopropane. This process of breaking a pi bond is an addition reaction.
Okay, so the first one that I want to talk about is hydrogenation. Hydrogenation is when hydrogen is added to alkenes to produce alkanes. The reverse reaction of this would be called dehydrogenation, and I mention this because that's an important reaction as well. But basically, this is a very simple one. You have a carbon-carbon double bond. You add hydrogen. Remember, hydrogen is diatomic, so you're going to have two hydrogen atoms. And those two hydrogen atoms attack at the pi bond, and they form this alkane. Hydrogenation is an important reaction. It is used commercially to convert vegetable oil to margarine or shortening. There was a time in the 90s that butter was bad, and margarine was good, but then they found out that, this stuff isn't really that great either. Turns out that hydrogenation leads to hydrogenated vegetable oils and hydrogenated fats, which then lead to something called trans fats, which are actually so bad for you, they're outlawed now. Second reaction that I want to tell you about is halogenation. The halogens, chlorine, bromine, iodine from the periodic table, they do the exact same thing as hydrogenation, right? So you have a carbon-carbon double bond. They add to a halogen, which is diatomic, which then produces the alkane, and this time it has halogens added to it instead of the hydrogen. Remember, this is different than the substitution reaction that we looked at earlier. The substitution reaction, you get a single bond stays single bond. An addition reaction, a double bond turns into a single bond. Also, in a substitution reaction, you're going to produce an acid because that hydrogen is going to need to come off and react with something. The third type of reaction is addition of a hydrogen halide. Hydrogen halides are also called acids, right? Hydrofluoric acid, hydrochloric, hydrobromic, hydroiodic acid. But basically, they're just a hydrogen and a halide, because if you can have hydrogenation and you can have halogenation, well, you can add one of each, right? So in these examples, we're adding HX. The X, like I said over here, represents the halide. So for example, this HX could be hydrochloric acid. The H goes to one side of the carbon-carbon double bond. The X goes to the other side of the carbon-carbon double bond. And this now becomes all single bonded. These can proceed in different ways, which I'm going to show you in just a second. Here is another example. We have a symmetrical molecule right here. HBr is going to be added to it. So the H goes to one side of the double bond and the Br goes to the other side of the double bond. These can happen in cyclical molecules as well. The H goes to one end. Notice there it's not drawn. That's something in, chemistry that we kind of have to get used to, that not always is there going to be a hydrogen shown there. We just sometimes have to imagine that it's there. And then the I goes to the other side of where that double bond was. So what happens if the molecule is not symmetrical, right? So this is an example of a symmetrical molecule. The H goes to one side, the Br goes to the other side. It really doesn't matter which way they go. But sometimes you have a molecule that is not symmetrical. Like, for example, this one here. So this side of the double bond has 2 hydrogens. This side of the double bond has 1 hydrogen and 1 carbon. These particular examples, I always suggest that students draw these all out because they're sometimes a little bit tricky to see when they're lined up like that. But anyways, you have to figure out what side the hydrogen is going to add to and what side the bromine is going to add to. And there is a rule, and this is called Markovnikov's rule. And Markovnikov's rule is a little bit tricky, but I think you can probably understand. Markovnikov's rule states, in the addition of a hydrogen halide to an alkane, the hydrogen adds to the carbon that already has the greater number of hydrogens. Okay? For some reason, this has always been called the rich get richer. All right? And wealth in this case is hydrogen. So let me walk you through this example. I like this one because it's all drawn out. So again, we have a carbon-carbon double bond, but it is not symmetrical. This carbon is bonded to 2 hydrogens. This carbon is bonded to a carbon and a hydrogen. So right away, if we were to decide which one of these carbons is richer, this is the rich carbon, okay? This is the one with the wealth, because again, the wealth is hydrogen. So when hydrogen bromide is added, the hydrogen is going to want to add to the rich side, and then the bromine is going to be left to the other side. We call this the major product. This is the minor product, not that it's not going to be formed, but it just won't be formed as much. So you can see here, here's another prediction. We've got an alkene, is this the same one? It's almost the same. Anyways, you've got hydrogens over here. This carbon is bonded to 2 carbons. So again, this is the rich side. So that's the side that the hydrogen is going to want to add to. So here you can see that became CH3, and this had to take in the Cl to it. This would be the minor product. That's why it says this one is not going to happen. I've got a video here that explains Markovnikov's rule. If you'd like to watch it, open up the notes and go ahead and click on it. It's okay, but it goes off on a bit of a tangent. The last type of reaction that I want to tell you about is hydration. Now, hydration is identical to adding a hydrogen halide, but in this case, we're adding water. Okay, so think about it like this. A hydrogen halide was HX, right? And the X represented some halogen, chlorine, bromine, iodine, whatever it is. Well, in this case, it's just hydrogen hydroxide. So the X is really just a hydroxide, okay? So if you think about it like that, it follows the exact same rules. This has to happen in the presence of an acid catalyst. This, by the way, guys, I usually write this stuff in here, but this is what you'll have to study in college. They call it mechanisms. But during hydration, water is added to produce an alcohol. It is reverse. The reverse of it is called dehydration, and again, more about that in the next chapter. So here you can see this is symmetrical, so we don't need to worry about Markovnikov's rule here. Ethylene, ethylene, by the way, is ethene, but this is a common name. Ethene reacts with water, in the presence of acid to produce ethanol. So again, hydrogen goes to one side, hydroxide goes to the other side. These reactions, like I said, they also follow Markovnikov's rule. So you can see here, this word that they use here is called more substituted. That's another word for it. But remember, I'm saying this side is the rich side. So that side has more hydrogens already. So when the hydrogen hydroxide attaches, otherwise known as water, the hydrogen is going to attach to the side that is already richer. This one, since it's cyclical, you'll have to kind of imagine what's coming off of it. This hydrogen here did not need to be drawn, but it was, which was kind of helpful. So this is the richer carbon here. So when the hydrogen adds, you can see that it adds there. Remember, when we're drawing cyclical molecules, one of the most annoying things about organic chemistry is that they do not need to show those.
That the double bond of the alkene breaks open, and the water, which, as you know, comes as an H and an OH attached to each other, that breaks open. OH attaches to one side, H attaches to the other. The trick is that whichever side has more bare hydrogens on it, like this carbon has 2 H's, this carbon doesn't have any H's attached directly to it. Whichever carbon has the most H's gets the bare H from the water. Here's what I mean. Let's take a look. We got our 2 carbons in the center connected to each other. The second one has 2 H's on it. The first one had a couple CH3s on it. Now notice I've rewritten the double bond as a single bond because we've broken open the double bond. That means we can attach something to each carbon. The carbon that has the most H's on it gets the H in this reaction, and the OH attaches to the other one. You end up with an alcohol. And actually the alcohol we've come up with here is, oh, I guess I don't know. I don't want to have to name it right now. But I do want to point out that you can also do this in the stick figure form of showing the molecules, right? You got a double bond between 2 carbons. The carbons obviously aren't shown because of the way this is drawn, but that becomes a single bond. These 2 single lines represent CH3s, and you end up with an OH attached to that carbon as well. Now an H gets attached to this carbon here, but you don't show it because it's one of these stick figure things. Long story short, alkene plus water equals alcohol. Best of luck.